Okay. Hello Year 12. Hopefully this is working. Hopefully you can hear me clearly. And hopefully you've been able to download the Shapes of Molecule worksheet that you see in front of you from Satchel 1. So last week I asked you to watch a series of videos by a different chemistry teacher. And in those videos they went through how to count the number of areas of electron density or bonding and non-bonding pairs within a simple covalent molecule, and from that number of bonding and non-bonding pairs to work out what shape a molecule will have. And all I'm going to do in this brief video is just run through some examples of molecules that you'll find with the different shapes, just briefly introduce why they have the shapes they have, and a quick reminder about things like the extra repulsion that non-bonding pairs have. So we start off with molecules that have two electron pairs and in particular two bonding pairs with no lone pairs. They form these linear shapes that you can see here, and an example might be something like beryllium chloride, so BeCl2, where the beryllium would be the centre atom and the chlorine atoms will be bonded at either end of the molecule. But an even more classic example of a linear molecule would be carbon dioxide, where each carbon atom is bonded to two oxygen atoms, but it forms two double covalent bonds, so a double covalent bond to each oxygen. That double covalent bond, those 4 electrons that are being shared between the carbon and each oxygen, they count as one area of electron density, so they count as one sort of source of repulsion between these electrons that are repelling one another. Okay. So next we look to 3 areas of electron density, 3 electron pairs, and if they're all bonding, you get this trigonal planar shape with a bond angle of 120 degrees. And again, a classic example of that might be boron trifluoride, BF3. But we've also got a couple of ions in there as well. Our nitrate 5 ion, NO3-, and our carbonate ion, CO3 2-. Now in a later explanation we'll go through a bit more detail about the bonding in those ions and how they come to be this trigonal planar shape, but there are examples for now. For the next one, for the bent shape with one lone pair of electrons, and you'll see that the bent name comes back again when we're looking at things like water with 2 lone pairs of electrons, but with one lone pair of electrons we end up with this bond angle of 118 degrees, and we could be looking at something like sulfur dioxide, SO2, but there's tin chloride as well, SnCl2, will also have these 2 covalent character bonds and a lone pair of electrons, and nitrogen dioxide as well, NO2. And again, we'll do a bit more detail about the bonding in some of those a bit later on. Okay, moving into 4 areas of electron density, or 4 electron pairs. We've got, first of all, the classic tetrahedral shape. I say classic tetrahedral shape because it's the basis of quite a few other shapes that you can see here. Has a bond angle of 109.5 degrees, and that's where all of the areas of electron density around that central carbon atom, or that central atom, sorry, they're all bonding pairs of electrons, so they all have identical repulsion from one another, and the furthest apart they can get is 109.5 degrees. So the sort of example that everyone knows of this is methane, CH4, but the ammonium ion, NH4+, with its dative covalent bond between nitrogen and one of those hydrogens, is another example. And the sulfate anion, SO4 2-, also forms this tetrahedral shape with a bond angle of 109.5. If we stick with 4 areas of electron density, but one of those is now a lone pair, so we've only got 3 bonds, we get the shape that ammonia, NH3, forms, but also phosphorus trichloride, PF3, or the oxonium ion, H3O+. And here, the lone pair at the top there, shown in this lobe with the 2 dots to show the 2 non-bonding electrons, that has an extra repulsive effect, and that makes the bond angle between these 3 remaining bonds here slightly smaller, lessens it by 2.5 degrees to 107 degrees. Take that effect a little bit further with 2 areas of electron density, with two lone pairs, and we end up with the bent shape that characterised water. And we'll learn later on that the shape of water and the fact that it's a bent molecule gives it the polarity that leads to such important properties of water. Okay, moving up to 5 areas of electron density, and when we have 5 bonding pairs, we have this shape here. Now this is called trigonal bipyramid or trigonal bipyramidal, and you might have seen in the previous videos that I asked you to watch why it sort of has this name for this shape. If you imagine drawing a pyramid down from this top atom to each of these 3 here, and then put a base on it, you'd have a triangular pyramid coming up to this point here. But you can also imagine a sort of mirror image reflection pointing down from these 3 atoms here down to the bottom one here. So you have 2 pyramids, one pointing up and one pointing down, hence bipyramid, and trigonal because it's a triangular based pyramid. Bond angles here, there are 2 of them, and that's up till now that's a little bit unusual. The 3 atoms around the central atom here that are sort of on the equator around the middle are 120 degrees away from each other, which you'd expect 3 equally repulsive pairs of electrons repelling to be 120 degrees. But because we now have these ones up and down as well, they have a bond angle of 90 degrees to the ones that are around the equator here. So examples, the best one that we have that breaks the octet would be something like PCl5 or PF5 that we've got here. Okay, no name for this next one, but effectively it's the same thing where one of those bonds has been replaced with a lone pair. So it could be one of the sort of polar ones pointing up or down, in this case pointing down, or it could be one of the ones around the equator here. Because this has an extra repulsive effect, you'll see that the bond angles have been lessened slightly. The ones around the centre on this side have been lessened to 119 degrees, and the bond angle between the one sticking out to the side and the one sticking up has gone from 90 down to 89 degrees. And that's, for simplicity, that's the same for either one of these. Okay. Examples of that might be SF4. SF4 might be your example for that one. In this next one, we've got 3 areas of electron density and 2 lone pairs. Now, if those lone pairs are above and below, so on this one in this position here and this position here, they both have an equally repelling effect on the 3 atoms or bonds that are around the central atom here, and so they don't cause these to flex up or down, so they stay exactly as they are, 120 degrees apart from one another, and we end up with this triangular planar shape like we saw when there were 3 areas of electron density up for things like BF3. However, if those lone pairs are in the sort of equatorial zone around the equator ones here rather than the up and down ones, they have an extra repulsive effect on all 3 of these and reduce the bond angle there to 89 degrees down from 90. So an example here might be ICl3, so iodine trichloride there. Finally, onto molecules that have 6 areas of electron density, 6 number of electron pairs. If they are all bonds, then we get this classic octahedral shape here. And you might be looking at that saying, hang on, 6, why is it octahedral? Well, if we were to, again, draw a pyramid, we'd have a square-based pyramid going up to this atom here with a flat base through the centre atom. So that would be a 4-faced shape. And then you'd have the mirror image, the sort of reflection in a puddle pointing down. Similarly, a 4-faced shape. And so altogether you'd have 8 faces, and hence that's an octahedral shape. If we replace one of these with a lone pair, we end up with this distorted square pyramid. So it's still like a normal pyramid, but the corners at the bottom here, rather than being flat, they are all pointing up ever so slightly by 1 degree because of the extra repelling effect of this lone pair of electrons here. Our example for that would be IF5. So you see the halogens feature quite a lot in here, and when we start to think more about their bonding, we'll understand a little bit more why they're able to form these different shapes. And finally, if we replace, from the octahedral structure, if we replace the 2 opposing bonds with lone pairs, And it doesn't matter which two, because of course if we rotate this molecule, it's the same thing, just looked at from a different angle. But if we imagine the top and the bottom one being replaced by lone pairs of electrons, they're both equally repelling, despite being more having a stronger repulsion than the bonding pairs of electrons around here, because they both have that extra repulsive effect, but they're both applying it equally to these ones around the middle. These ones around the middle don't change, so 90-degree bond angle for this. And this is square planar, and we learn about some exciting chemistry of molecules that have a square planar structure. There we go. So download the sheet, fill in your examples, and we'll do a little bit more of an explanation about why they have the shape they do in a future video. Thanks for your time.